All right, welcome to section 5.4. We're going to be looking at something called indefinite integrals. We've already defined definite integrals, but now we're looking at indefinite integrals. And we'll also be examining the net change theorem. Okay. So, let's go ahead and remind ourselves what a definite integral is. And we did that in a previous section of chapter 5. And that's when we're looking at integration from like 0 to 2 of x cubed, we'll say dx. And how we do this is we find an antiderivative and we evaluate it from 0 to 2. Okay, and then we plug in the upper limit of integration minus the lower limit of integration. And we get our solution. Okay, so the definite integral is a number, right? So it's a constant. And it represents a lot of things, but the most basic thing it represents is an area, right? The area under the curve x cubed from 0 to 2. Okay, so we can even do a little bit of a sketch, very basic sketch. Okay, so if this was our x cubed function, and let's say, not to scale, not doing the best job, but we're looking at something like this, then this definite integral is the area under this curve x cubed from 0 to 3. And we just determined that that area is 4. Okay, so what are we doing now in this section? Well, we're going to be looking at the indefinite integral. Forgot an I up here. The indefinite integral. And what's going to happen is we're going to have almost the same notation, but do you see what's missing? The limits of integration, right? So what's going to happen is we're just going to get a function. So we're going to look at the general, this is going to tell us to take the general, antiderivative. Okay, so this represents a family of functions. Whereas before, the definite integral was a constant or represented an area. And we call it a family of functions because C can be infinitely many things. It could be 1/4 x to the 4th plus 1. 1/4 x to the 4th minus a half, right? Et cetera, et cetera. And all those, that's called a family of functions. Okay, so another way to connect the two, the definite integral, how it connects to the indefinite integral, we definitely see that there is a connection because when we're taking the definite integral, that's one of the family of functions. So we can write this relationship between the definite integral and the indefinite integral. It's something like this. Okay, and that's what we saw before. So again, this indefinite integral right here represents the antiderivative, the family of functions. It really represents all antiderivatives. And then we evaluate that from A to B. All right, so that's how we relate the definite integral to the indefinite integral. Okay. So in your textbook, on page 403, there's a table of indefinite integrals. And we've looked at some of them before when we were looking at definite, or antiderivatives rather. But so now we're looking at this with different notation. And let me go ahead and pull this up. This is just a little snip from your textbook. Okay. And again, we did this with the antiderivatives as well. All right. So go ahead and look at your textbook for that. And, we can just pick on one. So, something like this, the integral of a constant is equal to kx, right? And again, this is the antiderivative because the derivative of kx is just k, that constant, okay? Likewise here, this is telling us to find the family of functions, the general antiderivative of cosine, and it's sine x plus c because the derivative of sine x plus c is cosine. Okay, and they have more complicated ones. They have your inverse functions and your trig functions, stuff like that. All right, so let's see what we're going to do with that information. Let's practice. So let's say we want to find the indefinite integral of 1 over x squared dx. Okay, well, when I'm thinking of 1 over x squared, whenever we take our derivatives, whenever we take the antiderivative, whenever we take the integral, it's always important to remember if there's any discontinuities. Okay, and because that's one of the things. If we want to take the indefinite integral, if we want to take the derivative, stuff like that, it's not always defined on discontinuities. So at 1 over x squared, x can't be 0. Okay, so we have this asymptote right there. So I'm going to write that. There's a discontinuity at x equals 0. But when we go to write the general antiderivative, all right, so remember we can always think of this, add this little intermediate step. 1 over x squared is like x to the negative 2. So when we take the general antiderivative, we add 1 to the exponent, and then 1 over the new exponent. In this case, it's just going to be negative. And for us, because it's the indefinite integral, we're just going to say plus c. There's no limits of integration, all right? So we're looking at negative 1 over x plus c. And as far as this discontinuity at x equals 0, this indefinite integral is found with that understanding. So we don't really have to notate it. So we don't have to worry too much about discontinuities when finding the indefinite integral. So with the understanding that it's valid or true on, however you want to say x not equal to 0. I'll use interval notation. Just take that 0 out. Okay, so let's do some more examples. So that was our first example. What do we do when a function's not continuous on the real numbers? Well, we still find the indefinite integral. There's just an understanding of the implied domain. So let's look at some other examples.